affine plane. So you have this n-dimensional affine variety. This is Noether lemma. It's very important because this gives you some understanding of, for instance, suppose you want to prove there are smooth points in a given algebraic variety. You can do it without Noether lemma. Also, if you want to do to prove Hilbert Nullstellensatz, and you don't want to use what we did, set theory, you also need Noether lemma. So it's important result, and it makes geometric, it has geometric meaning. Okay, so to understand this, you have to understand lots of things. In particular, you have to understand what is called finite maps, which is like ramified covering with finitely many preimages. And this is what we shall do. So the typical example, and in fact, the most important example of finite maps is a group quotient. So you have a finite group acting on a affine manifold. You want to take a quotient. So this is what we shall do. And again, over C, for simplicity, you don't need it over C. So all what I'm giving you today, it makes sense in non-zero characteristic. But for simplicity, I am doing it over C, because otherwise it's sort of hard to have geometric sense of what happens. Okay, so today I will prove this result, which is theorem of Noether. That if you have a ring R and G finite group acting on R by automorphism, so G sits in automorphisms of R, you can take invariant RG is a set O ring of O in G invariant elements. This is RG is the set of all R inside your ring, such that G of R is R for all G inside G. This is what invariant means. And if R is finitely generated means it's a quotient of polynomials, finite dimensional polynomials, then RG is finitely generated. So invariant theory was one of the central subjects in algebra and in mathematics in 19th century. And what people did, they started with some group, some action, and they wrote explicitly the Hilbert basis. I mean, the generators. And of course, Hilbert basis theorem sort of did it for all situations, and people were very angry. But because they spent so much time writing explicit bases, the typical paper of Marx Noether was like 200 pages of computations with explicit polynomial bases. And Hilbert did it non-explicitly, but generally. So they were angry and unhappy, but in the end, it was Emmy Noether who did it axiomatically in a very formal way, because Hilbert did it explicitly as well. So we shall do that the way she did, very formally and like axiomatically. Of course, you can do it informally. So let's do it like, for example, let me give you an example where it works. So you have C2, quotient by plus minus 1. So you have a group, plus minus 1, acting here by plus minus 1. So it's, This is a statement about algebra. It's sort of hard to translate it into a statement about geometry, because then we have to sort of identify points with the quotient. But since this is an example, it's sort of easy. So now functions. So you have, so let's call this group G. G is just plus minus 1. It's Z by 2. And it acts here by plus minus 1. Am I clear? So now we're interested in we have R, just polynomial functions on C2, which is C of xy. It's polynomial of two variables. This is regular functions on C2. On C2. And then you have invariant, so G invariant polynomials is the same as even polynomials. Do you know what is even polynomial? No one? So P is even if P of x is equal to P of minus x. So it's like parabola, square parabola or fourth degree parabola as opposed to third degree. And then P of x, y is even if it is a sum of monomials of even degree. Because if you have monomial of odd degree, it goes to minus. Monomial of even degree goes to itself, right? Then what is monomials of even degree? They're generated by x squared, y squared, and xy. So generated by, in fact, you can even write the relations. It's not hard, well, it's not immediately obvious, it's an exercise for you to show that all even monomials are generated by x squared, y squared, and xy. The idea is, okay, you have even monomial, it has x2 divided by x2, something which it has a y2 divided by y2, and if it has no y, then it is xy. That's all. And then let's call this A, call this B, call this C. Then you have a relation, the only relation, in fact, which is A, B is C squared. So this is the ring of invariants. We obtained that RG is C of A, B, C. This is the ring of polynomials, generators. I'm explaining what is a ring of even polynomials of two variables. So you have A, B, C, which are generators, and you have the only relations, A, B is C squared. That's all. Quadric. So this quotient is just this quadric. What I will do now, I will prove the same, but for general group actions. Okay, so what is representation? So how many of you have done representations of finite groups? None. You did. And like, who knows that finite groups representations are semi-simple? Okay, I will acquaint you with the representations. I mean, I don't give you the whole. There's actually a very good book, which I really, it's very elementary and it should be read by anybody in the first undergraduate. I mean, at least for the first year of graduate school, but in fact you can read it as undergraduate. This is SER, representations of finite groups. It's a very small, very nice, very readable book. Everybody should read it. Okay, so definition. Suppose you have V vector space. G group. Then V is So representation of G on V is a map, a homomorphism from G to the group of matrices. GL of V is a group of matrices where GL of V is group of invertible matrices. So I am interested only in representations over C or R, but C actually doesn't do any representations in final characteristic because it's really complicated. I mean, it's one of the most, it's still, there are lots of open questions even now. But for the characteristic 0, everything by now is known. In fact, it was known since Schur and, well, Sir. Okay, so you have a homomorphism. In that case, V is a representation space, or just representation. Now we're interested in sub-representations. This is category. I mean, the representations, the homomorphism of representations are maps which commute with G actions. So homomorphism of representations are maps V to W commuting, linear maps commuting with G action. So each element of G acts on V in a way which is compatible with the way it acts on G. Should I explain what is compatible, or is it clear? Everybody? Who wants me to explain that what is compatible, what compatible means? Who doesn't want me to explain this? Okay. I probably should do that. So you have a map to W. You have element G, which also maps from V to V, and the same map of G maps from V to W. This is because G acts linearly on V and on W. This should commute for all G inside your loop. This means that they're compatible. So the way it acts on V, the way it acts on W is the same. Okay, sub-representation. Is just G-invariant subspace. So definition, W inside V is G-invariant subspace if for each G inside your group G, G of W sits inside W, and in that case, W is called subrepresentation. Okay. And then definition, V is irreducible if it has no subrepresentation, non-trivial subrepresentation. So it has trivial W and 0, but no non-trivial subrepresentations. Okay, so the main result about the representations of finite groups is that there are finitely many irreducible representations, and in fact, just as many as there are left classes. I mean, there are adjoint classes of the group action on, yeah. So, but this doesn't matter. I'm not going to use or to explain this. What I'm going to do is just to show that a semi-simple representation. V is semi-simple if it is direct sum of simple representations, or irreducible. Irreducible is the same as simple. Direct sum of irreducible representations. So, for example, over R, you can have R2 with action of rotations. Say Z by N acts by rotations by 2 pi by N. This is clearly irreducible because you don't have any one-dimensional subspaces which are preserved by rotations. This is an example of representations over R. Of course, if you tensor this by C, it stops being irreducible, because if you tensor R2 by C, you obtain C2, where this acts with Z by N acting with two eigenvalues as square rotation. So it's exponent of 2 pi square of minus 1 by N, and here you have exponent of minus 2 pi square of minus 1 by N. It's not obvious, but this is one of the things which happens in representation theory. You have something irreducible, you tensor it by C, no longer irreducible. It splits. Okay, the most important theorem about representation in finite group is that they're all semi-simple. This is something. Do you know about tensor products? So you can think about metric as of a tensor on the representation space, like 2 form. And then invariant metric is just invariant tensor. On the other hand, you can just say the definition, a metric, a quadratic form, on V is G invariant, so let's call it is invariant, if for all G inside your group G, H of Gx, Gy is equal to H of xy, and for all x and y inside the vector space V. For all of this, you have this. This means that the metric is G invariant. Of course, the metric can be Hermitian and not, it will be quadratic form, but not linear, not C-linear, but linear over R. So who of you know what is Hermitian form on a vector space? Huh? What happened? Okay, it works. Who knows what is Hermitian form? Please raise your hand. Yeah. Next time I will bring a couple of slides about Hermitian forms. But it is something that people use all the time. So if you have, over reals, you have Euclidean forms, the metrics, the positive definite bilinear symmetric forms. Over complex, you have Hermitian forms. So by definition, Hermitian form on complex vector space is H of vector space V is H, which takes V times V to C. So it's bilinear, R bilinear. So it's bilinear over R in the sense that if you multiply this guy by real, the result will be multiplied by real. R bilinear, and with the following properties. So H of X is positive and real. Positive if X is non-zero. And second, of course, this means that if you multiply this by some complex number, this should be multiplied by different complex number. I mean, if you multiply, this can't be complex linear because complex linear would be, wouldn't have this property. So the second is H of lambda X. X is equal to H of X, Y. X lambda bar Y is equal to lambda H of X, Y. In other words, it's linear on the first and antilinear on the second argument. Antilinear in the sense that you have to add complex conjugation. So in other words, H of X lambda Y is equal to lambda bar H of X, Y. So it is a Euclidean metric which has this nice complex property. So it's also invariant under complex rotation. So if you have, yes, if you have a complex rotation, lambda in C, absolute value of lambda is equal 1, then H of X, lambda X and lambda Y is the same as lambda bar H of X, Y. But lambda bar is absolute value, so this is the same as H of X, Y. And in fact, you can prove, I'm not going to prove that today, but it's really true that Hermitian metrics are the same as just rotation invariant positive definite scalar products. Okay. So the idea is that if you work over R, the scalar product works. If you want to work over C, you have to do the Hermitian metrics. So yeah, and of course, if you have a, so this is again an exercise or remark. So the idea is that you know that for each real vector space with scalar product, there exists a basis in which the scalar product is orthonormal, right? So for each Rn, for each vector space V is Rn, H scalar product, there exists a basis orthonormal such that H of some lambda I basis EI. EI sum of mu I EI is equal to sum lambda I mu I. How you get it? You just take any vector, you multiply it by a number, so it's squared to 1, its square is 1, and you take orthogonal complement, and you apply the same argument to this orthogonal complement, which is smaller dimension. And then if for each vector, the same is true for complex vector space, the proof is literally the same. Cn H Hermitian, there exists a basis EI, also called orthonormal, such that H, so here lambda I, mu I are reals. Now you will have the same but for complex. So this will be sum of lambda I EI, sum of mu I EI, and lambda I mu I are complex numbers. And this will be equal to the same sum but with complex conjugate. So it's lambda I mu I bar. And this is sort of immediate follows from the axioms and the same argument. So you start with a vector, you take a term complement, which will be also complex vector space, Hermitian, and you repeat. Yes? So if you speak of Hermitian forms, they are over R, yeah. They're not R linear, they're not complex linear. They're only, the Hermitian forms are not complex linear. They're linear only over reals.
Oh, I mean, for this, like, for the tensor, you R2, tensor by C.
Yeah, so it's tensor R2 by C. So you do this. Thank you. Okay. So this was Hermitian forms. Now you have an observation. So it's a lemma. You take V vector space over reals or over C. H Euclidean or Hermitian form, scalar product. So Hermitian forms are also called Hermitian scalar products. So it's real or Hermitian. Then if G acts, so you have representation, G acts on V, representation, then you can write for each G inside the group G, you have to write G of H of xy is H of G of x, G of y. This is the way the group acts on Hermitian or real scalar products. And then we have the following sum. 1 over absolute the cardinality of G, G of H, over all G inside the group. This is now invariant. So this is invariant metric. Indeed, how do we check that it is invariant? Let's act on it by some element. So it have G1 inside your group G, and then we want to act. So let's call this average over G of H. So this is averaging over G in the sense that we act by G and we take average. And then you take G1 of average of H over G, and this will give you sum of G1 G of H. Here I have again G inside the group G, and here I have 1 over absolute y over cardinality of G. Good. This is the same set as this. You just interchange some summands, but the sum is the same. So this is the same as average G of H. This is the key observation, and this is why you need characteristic 0, in fact, because otherwise this won't work. And also you need positivity, because, I mean, if you have just any scalar, I mean, not positive definite scalar product, just any non-degenerate form, you can add them together and take 0. But since this is positive definite, this is positive on all non-zero x's, and then you sum that up, the sum is also positive. The sum of positive things is positive. So this is non-degenerate scalar product. So we obtain the following observation, which is on the next slide. I'm just doing something. So this is, oh no. It was on the previous slide. No? Where it was? It was definitely somewhere here. Okay, it was there. So, yeah. So corollary, or it's just because of sum of two Hermitian is Hermitian, and then there's many of them. So let's call it claim. Claim any. So let's G be a finite group. Any G representation over R or C admits as G invariant scalar product, real or real or emission. Yeah. So what was right? So this was, yeah, this is the notion of G invariancy, and this is the main result. And this is something that probably Frobenius already knew. So probably this comes back to Frobenius. Okay, now if you have a subrepresentation, remark, if W inside G subrepresentation and H G invariant metric, then V orthogonal complement is G invariant. Should I explain this? So for whom of you it is clear already? Not to everybody. Okay. So proof. So X belongs to W orthogonal if and only if for each Y inside W, H of X, Y is equal to 0. That's the definition. But then this is equivalent to, because H is invariant, to H of Gx, Gy is equal to 0 for each G inside the group. But then this vector is inside W. And Gx bijectively. So this implies that H of Gx Y prime is equal to 0 for all Y prime inside W. We just write Y is equal to G minus 1 Y prime. So if it is orthogonal to all elements if X is orthogonal to all elements of W, then Gx is orthogonal to all elements of W and vice versa. This is equivalent. And this is why X is, why this space is G invariant. Because for each element in this orthogonal complement, G of it is also orthogonal. Okay, and this has a nice corollary. As a corollary, so let G finite group, each G representation over C or R is semi-simple. In fact, you don't need C or R. If you write Q, you can also do the same. I mean, the same argument works slightly. Doesn't matter. So it's enough to have finite characteristic. As a proof, we want it to be direct sum of irreducible representations. Take, let's use induction. So suppose, of course, find dimensional. I didn't write find dimensional. It's assumed. So all vector spaces, unless I explicitly want them to be infinite dimensional or find dimensional. So suppose this is true. This is true for all V with dimension of V less than n. For dimension 1, it is clear, so we have basis of induction is obvious. Then, if you have V non-irreducible, then V is direct sum of W plus W orthogonal. And this and that direct sum of irreducibles by induction. So every representation is semi-simple. This is important. The same is true for compact Lie groups. The argument is similar. Instead of sum, you take averaging. But it's, of course, false for infinite groups and for non-compact Lie groups. So I can give you an example very easily. When it is not true. So I should erase something. I would probably erase this. So example when it is not true. So you have a group Z when it's false, non-semi-simple. So you have Z acts on C2 by these matrices 1, 1, 0, and here you have n, where n belongs to Z. It's not hard to see that this is a group. You just multiply two such matrices, and then n is multiplied by, is added, right? So if you have, let's call this an, then an multiplied by an is an plus m. So this is a representation of a group. You embed a group into the group of matrices. Yeah, but it has a first it has a it's not irreducible. It has a sub-representation, namely there is a vector where these matrices act by identity, one of the basis vectors. So it acts an of x is equal x, and an of y is equal to nx plus y. This is X. But then it is not semi-simple because you start with this X. You want to have some other sub-representation with Zx, but there is no sub-representation where Zx, Z moves. If you look at like it starts with a square and it shifts it by it moves it to this the diamond, this parallelogram. So it cannot have any. It has only one-dimensional sub-representation, namely this. The rest of sub-representations, the rest of lines are shifted, right? I mean, every line is just moved, except this X line. The rest of the lines are moved by the group action. So this means that this is not an irreducible representation. Was I clear? So who knew that already? Okay, sorry that I did something that you know, but you say I have to. Okay, but for finite groups, this is not true. For instance, if you have a rotation, it's irreducible, and you can actually prove that over C, any commutative group has just, we shall use it at some point, so we shall prove it, probably. Any commutative group has one-dimensional irreducible representations. Okay. This was, now let me give you something about well, not exact functors, but just functors first. There's, okay, it's sort of different order. Yeah, so let me give you in 1 minute, and then I will return to exact functors. Yeah, so there's on representations, on group representations, there are two important functors, mapping them into vector spaces. They're different. So invariance, so if you have V representation of G, invariance is, I denote this by Vg with the top. So Vg is all vectors inside this invariance, all vectors inside V, such that Vg of V is equal V for all G inside the group. This is something I already gave to you, but then there's also coinvariance. Coinvariance, Vg with the G below. This is a quotient, so this is V quotient by the subspace generated by X minus G, X for all G inside the group. These are different functors. For instance, let me give you an example when they're really, really, really different. So example, this examines Z action. Z acts on, but now on infinite dimensional space, on a vector space generated by, say, X by all xi where I inside Z. And it acts by shift. So N, so let's call it rho, is an action from Z to GL of this vector space, this infinite dimensional vector space with the basis xi where I inside Z. So you have rho from Z to GL of this vector space, which takes a rho of N. It takes xi and moves it to xi plus n. It's a shift. It's acting by shift, shifting your basis back and forth. Am I clear? So you have infinite dimensional space with the basis numbered by integers, and you have shifts. Yes, you have a question.
V lower g, that's the sense of all orbits, this quotient.
No, this is the vector space generated by this basis. So this is basis. Sorry?
V lower g, the definition of co-invariant.
Co-invariance. This is a quotient, again, by the vector space generated by these guys.
So they are equivalent classes of orbits.
You can say so, but this is vector space. It's not entirely orbits. But if two vectors are in the same orbits, they are identified in co-invariance. So you take, so this you take quotient by, you identify vectors in the same orbit. And then you take the quotient by this identification. But you do it in vector space. So that you take a vector space V and divide it by the subspace generated by these vectors. So it's for all x inside the vector space. And I want to give you an example that this is two different functors. So example, I gave you this basis. So let's compute the invariant. So there are no invariants. If you have a sum of xi lambda I inside R or C doesn't matter. This is shifted, but this is finite sum by Z. If you have a finite sum, you can shift it so far that it doesn't, this sum doesn't intersect. So this is no invariance. And there's a co-invariant, namely the map sum of xi lambda I. You have a functional mapping it to sum of lambda I. So it's a map from V to R or C, doesn't matter, which is G invariant. And this is clearly a functional on this co-invariant space, which is non-zero. So the co-invariant space is non-zero. So if you, in fact, this is the co-invariance. You can prove that this map is just the projection to the co-invariant map, but I'm not going to prove it. I just want to explain to you that these two notions are non-trivial, different. Okay, now the important thing is that they are not, in fact, different for finite groups. Again, over C, it's false over, it's true only in characteristic 0. It's false for P, characteristic P. So theorem, suppose that V is a representation of finite group over C or over R, and again finite dimensional, then VG invariants are the same as co-invariants. Well, you obviously have a map from invariants to co-invariants. So natural map, just projection, then the natural projection from invariants to co-invariants is isomorphism. Okay, so let me give you the proof. It's not hard. So suppose that V is irreducible, non-trivial. then there are no invariants. Because this is a sub-representation, then because Vg inside V is sub-representation. And this sub-representation can be the whole thing because it's non-trivial representation, right? Am I clear? It should be trivial, so let me repeat. You have a reducible non-trivial representation. I want to prove that invariants are trivial. Indeed, invariants, it's just the subspace of vectors which are fixed by your group. It's a sub-representation. But there are no, it's irreducible. It has no non-trivial sub-representation. It's either everything or zero, and it can be everything because it's non-trivial. And then Vg is equal to 0 because the subspace generated by x minus gx, a subspace, is a sub-representation. Indeed, if you act by h on it, well, by g prime, you will have g prime minus g prime g. So it is a sub-representation, and so what is this subspace? It's, as you said, this is a subspace generated by difference of vectors which live in the same orbit. Of course, if a group acts on its orbit, so if you have two vectors in the same orbit, you shifted them by the group action, they are again in the same orbit. So this is also sub-representation, but it's non-trivial, because it's non-trivial representation. So it should be everything. So this is equal to V. And then the co-invariants are also trivial sub-representation. Okay, this was for and of course, if now you have any representation. For any representation, G representation, you have G is the direct sum of Vi, where Vi are irreducible. Yeah, by the way, invariants are Vg dual is the same as V dual G. This is why they're called invariants and co-invariants. It's easy to see that they're, at least for fine dimensional spaces, these two guys are just dual. This is the reason why it is called co-invariants. It doesn't matter, just to explain the terminology. Okay, so this is, you have representation. It's direct sum of irreducible. And then Vig is equal to Vig equal to 0, where Vi is non-trivial, because it's irreducible. And then Vig is equal to Vig is equal to Vi if Vi is trivial. Because there is no action on trivial, so this x minus jx is always 0, and everything is invariant. So then you act by these two functors on this direct sum. You just remove all non-trivial components, and you leave trivial components where they are. So this is really natural map, which is equivalence of factors. I mean, it's just identity. Okay. Now for exact functors. Something we shall use every time, and if you do algebraic geometry, it's something, I mean, this is a central notion, in fact, for the whole algebraic geometric business. It's due to Grothendieck, obviously. Yeah. It works for what is called abelian category. I'm not defining abelian category because you don't need that, but at some point you shall definitely need that in more generality that I give. I just give it for models over groups, models over rings, for vector spaces. So G representation is the same as model over the group ring. C or R or whatever. Do you know what it is? No? Who knows? So this is the ring of the sums lambda I Gi, where Gi belongs to the group, lambda I belongs to the vector, to our field like C, and you multiply. So sum of Gi lambda I Gi multiplied by sum of mu I mu j Gj is equal to the sum lambda I mu j Gi Gj. Just you multiply group elements together and you multiply the coefficients as the coefficients. It's sort of clear that if you have G representation, you have a model over this algebra, and converse is also true. It's not an algebra in the sense I would usually use. It's not commutative, but it's still an algebra, and first it is clear that if you have an algebra over this, you have group action because group is embedded into there multiplicatively. So it sits in this algebra as multiplicative subset. On the other hand, if you have a group representation, you can act by these sums, multiplying by the group and summing up. So I don't want to define abelian categories. I just say that, OK, we work over models. And since representations are also models, it makes sense. This is the only time in the first half of the course, and probably the whole course, where I use something except the models over a commutative ring. Here the ring is non-commutative, but still the exact functors make sense. So let me define them. So definition. Suppose I have a functor from category C1 to C2, functor on categories of R models. Could be the same category, in fact, category of R models. I think we shall use only this, but it makes sense generally. F is called right exact. By the way, do you know what is exact sequence? Who knows what is exact sequence? Oh, very good. Almost everybody. So exact sequence is very simple. It's if each exact sequence, you have A goes to B, goes to C, goes to 0, and here I have 0. This means that A sits inside B, so this is embedding, and this is surjection, and C is a quotient of B by A. Okay, if each exact sequence is mapped to, so it's right exact, right? A goes to B, goes to C, goes to 0. So here, this is not necessarily embedding, but the rest is true. B is a quotient of, C is a quotient of B by A. And left exact? Left exact. If, again, it's exact from the left, so it's this mapped. Sorry, it should be F, 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 because we put F here. If mapped to 0 goes to FA, goes to FB, goes to FC. Here it should be embedding, and this FC, yeah. And the kernel of this map should be equal to FA. Okay, and now we should probably make a break because it's time. Sorry for being late, but there is a problem, like exercise for you, that prove that the invariance is left exact and co-invariants are right exact. And you can go for 5 minutes until 14:38. And please come back. Exactness of invariance and co-invariance. Anybody? It's not hard. Let me give you, explain why it is true. Sorry? In which sense? Could be, yeah, could be. I don't remember. But it looks quite plausible. Okay, so you have A, representation goes to B, goes to C, goes to 0. Here you have 0. And we take invariance, AV, AG. So they have BG. This is clearly an embedding because, I mean, this sits in there. This sits in there. So this is just invariant vector goes to invariant. This was embedding. This is an embedding. Good. Now you have CG. You want to, it's clearly non-surjective. I mean, you can see this non-surjectivity in the example I gave with the Z action. It's an exercise for you to prove that it is non-surjective for this two-dimensional space with Z action which I gave with the action, this kind of action. But this is still true. So what is the kernel of this map? This is vectors which go to 0 under C. But these vectors come from A, and they're invariant. So they came from AG. Clear. Now let's do this co-invariance. You have AG, BG, CG. Okay, here this is a quotient. This is a quotient of C. B acts surjectively to C, and this has to be surjective to there. This diagram is commutative, so this has to be surjective there. This is also surjective by definition. Questions? So this is surjective. Now, if you have something which goes to 0 under this map, this means that, I mean, this is surjective, so it goes to a kernel of this map. Sorry, yeah. If something goes to 0 under this map, it is mapped to kernel of this map. But then, well, you can check. Probably it's easier to check that if you really prove that VG dual is V dual G. So duality changes invariance and co-invariance, and then, well, I will leave it as an exercise. It's easy. It's what is called diagram chasing. You start with a vector, you suppose it goes to 0, you check that it comes from here, you check that it actually comes from the vector which is mapped to 0 by if vector goes to 0 under this map, it comes from this map, and it goes to it because then it goes from this map. Anyway, you have to do it yourself. Now, what is important for us that for finite group this functor is actually exact. And you don't need this. This obviously follows from this exercise and what I proved for invariance and co-invariance, because one of them is left exact, another is right exact, and they are the same for finite groups. But then you don't need that. Suppose you have a map of finite group representation. B goes to C, goes to 0. You have A. This is all direct sum of AI, which are irreducible. This is direct sum of BI, which are reducible. This is direct sum of CI, which are irreducible. So you can start decompose this BI onto direct sum of representations by starting with direct sum of CAI. So instead of that, you can say write direct sum of AI and then direct sum of BI prime. You have this irreducible decomposition, you map it to here, you take orthogonal complement, you obtain the direct sum for the rest. And of course, this goes to 0, and this is mapped onto direct sum, so it will be direct sum of BI prime. This would be the irreducible decomposition for this representation. This should be clear, right? Again, you start with the irreducible decomposition for A, you obtain the irreducible decomposition from B, where you just take a orthogonal complement to A and decompose it, and this would give you the irreducible decomposition for C. Okay, now we apply our functor, invariance or co-invariance, doesn't matter. This will be a direct sum of all trivial representations, AI trivial, like G. They're either 0 or non-zero, but then you will have the same AI G plus BI prime G. And here we'll have direct sum of BI prime G. You just remove all non-trivial representations. And the trivial representation also form exact sequence because there are just as many here and there.
Here, if you have the exact sequence of semi-simple representation, and so their reducible components are equal. I mean, the number of...
Yeah. This is how we obtain it. So we take direct sum of AI, irreducible decomposition, we put it into B, and we take orthogonal complement to it, which will be direct sum of BI prime. This is again direct sum of irreducible decomposition, which is mapped to C identically. So C is direct sum of BI prime. But then you have, after you apply this functor, you have the same here and the same here, so it's really an exact sequence. And this is something I will use a lot. And in fact, you can write this functor explicitly. So V goes to VG as follows. So V goes to the sum. Again, it's the same sum as we already had. 1 over G cardinality, sum G inside the group G of V. This is called averaging map. So this map is maps into any vector into invariant vector. This is something we have already discussed. It acts as identity on invariant vectors, and it projects everything to invariance. So it's just this projection to co-invariance, for instance, or to invariance. But in fact, since this is projection, you should really think of it as projection to co-invariance, because it is. So this is averaging map, and yeah. So now let's discuss about actions of group on the affine varieties. So as we discussed, affine varieties are the same as rings. So by definition, action of G on affine variety A is homomorphism from G to automorphisms of the ring of regular functions on A, where OA is a ring of regular or polynomial on A. Of course, these categories are equivalent, category of affine spaces and category of rings without nilpotence and finally generated. So this is really the same as action on the variety. And then we want to define quotient space. We can do that by using Nullstellensatz. But then for that, so by sort of the idea, A quotient by G should be equal to spectrum, to the variety corresponding to the group, to the ring OA of invariants. This is something we did for C2 quotient by plus minus 1. We are interested in the corresponding ring, but we don't know if it is finally generated. This is something I was going to do today. I'm not sure I will have time. Maybe we should continue next time, but let's try. And of course, then we need to identify the maximal ideals in the quotient with the maximal ideals in the invariant space. I mean, the points in the quotient with maximal ideals in the invariant space. This is not something I was not going to do today, definitely. I was going to do today is prove Noether theorem that the invariant group, the invariant ring is finally generated. So, theorem of Noether. So if you have a G acts on affine group, acts on finally generated ring R, then the invariance ring, the ring of invariance, is finally generated. And the proof is the following. So scheme of the proof. We start that proving that RG is Noetherian. This is already non-trivial, of course. But it's true in some generality. Then we prove, so the first, second proof that RG is finally generated for polynomial ring, for R polynomial ring. So we prove that this is actually the probably the generality which was needed to Emmy Noether when she proved this theorem. And then the third, which is not hard, the deduce general case from polynomial. Okay. I'm running out of time. No, I might be able to do it. So first, let's discuss ideals. We want to prove noetherianity. This is done by thinking about ideals in the ring and the ring of RG. And I claim that ideals in RG are embedded to ideals of R. If it is true, then noetherianity is clear, because what is noetherianity? This is noetherian ring if any chain of ideals stabilizes. But then if we have an embedding, then it stabilizes. How to do that? There's a lemma. For that, I will use averaging map. So if you have I, an ideal in the invariant, I work on these assumptions. So I have an ideal in the ring of invariants. Then I do averaging of Ri. Ri is corresponding ideal in R. I average that with D. It will be equal to I. Notation is right. Yeah. Proof is trivial. Okay. We take averaging of with G of Ri. I is already G invariant. So this is the same as averaging with G of R times I. This is invariant, you can move it around. And this is the same as RG, because invariants are the same as coinvariants, times I. And this is the same as I, because I is an ideal. Okay, noetherianity is clear then, because if you have infinite chain of ideals, like I1, subset I2, subset and so on, this is all in RG. This gives you a chain of ideals, Ri1, inside Ri2, inside and so on, in R. If this chain is, this chain has to stabilize because R is noetherian. But then you can recover from this chain by applying averaging. So if this stabilizes, this also stabilizes. Then R noetherian implies that RG is also noetherian. Okay. Was I clear? Okay. We did with noetherianity. Now graded rings. Did you have any graded rings before? Who knows graded rings? Almost everybody. So graded rings, it's written there. It's just a ring which is direct sum of graded components, and then the graded components are multiplicative. So if you have, the typical example is polynomial ring. Polynomial ring is graded by the degree of the polynomial. But then you have other graded rings, of course. Like today we had the rings of even polynomials. It's also graded by even numbers. But it's not polynomial. Okay, now we have, did we have a definition? Yes, graded finite type. Finite type is where you have all components are finite dimensional. It's a pity. Do you want me to continue next time, or do you want me to take extra 5-10 minutes? Who wants me to continue next time? Who wants me to take extra 5 minutes? Okay, thank you very much. It's good because I really don't want to repeat the whole thing. Now definition. A direct sum of AI, graded ring is called a finite type if all AI are finite dimensional. like polynomials. I mean, polynomials of given degree are finite dimensional. Or even polynomials. This is another graded ring, which is also even finite type. Now, important thing, that neutrality is finally generated for graded ring of finite type. So this is claim 1. A star graded is Noetherian if and only if it is finite type. See, it's proof slightly long, but it is almost easy. So yeah, finally generated, sorry. I am going out of time, so I'm doing errors. So it's graded Noetherian ring of finite type. There is really a source of huge confusion here, because there is finitely generated, there are two notions, finitely generated ideals. This is like models, finitely generated. There's finitely generated rings. Ideals are generated additively and rings multiplicatively. It's really confusing. So you should always take care which finitely generated you mean. Okay, but let's do it slowly and let's prove this claim. Finitely graded, finitely generated, Noetherian is finitely generated. The converse is obviously true, because if what is finitely generated graded ring? It's just a quotient of polynomial ring by some ideal, probably graded because everything is graded. It's obviously finitely finite type, because polynomial is finite type, it's a quotient of polynomials. And then there's also Noetherian, because the quotient of polynomials are Noetherian, quotient of Noetherian is Noetherian. So this implication is clear. This is clear. This one. So we're interested only from finite type, and Noetherian obtained that it's finitely generated. And the idea is that, okay, suppose it's not finitely generated. You start with some finite number of generators, you add more and more, and this gives you an increasing ideals, chain of ideals inside, and what is called augmentation ideal, namely the ideal of things of positive grading. Okay, so this is the idea. Now let's prove it. So one direction is clear, so we can assume that it is finite type and Noetherian. So proof that Noetherian implies finitely generated ring. So we have an ideal I, which is just direct sum of positive generated, of positive graded guys. This ideal is finitely generated ideal. This is already confusing. This is another finite generated notion, different from the finite generated of the ring. I'm sorry about that. Okay, so you have A1 dot AN generators. Then we want to prove that everything is generated by these guys. You have to take care. So we do N is the maximal grading of this AI. So typically this AI can be sum of some graded components. So we take the maximal graded, the maximal number of the maximal graded components. And we take direct sum of all AI, which are I less than equal or equal to N. This already generates A. Why? Because if you have, well, to prove you use induction, so you assume that you take the smallest, you take the smallest grade degree, which is not generated by these guys. We take, how it is, Z, let Z Z be smallest degree element not generated by this. This is finite dimensional, so AI are its generators, its basis. This is finite dimensional space, so we can take its basis. We take Z smallest degree element not generated by this AI multiplicatively. So we take the products of these guys, but then it is Z is a sum of Fi, AI. Fi belongs to the Tor ring, right? Because this is also generators of our ideal. And Fi has smaller degree because AI has positive degree than Z. They are generated already by induction assumption. So this is all generated by AIs. That's all. OK, now the last slide. So I need to prove the Noether, well, not the last slide. Noether theorem for polynomial invariance. It's easy. So Noether for polynomial invariance. So we need to prove that you have C Z1 dot Zn G is finitely generated. Right? OK, so this is Noetherian, as we proved, and this finite type. Finite type and Noetherian. It's finite type, Noetherian, by claim 1, then it's finitely generated. Clear? So we take invariant of the group action inside the polynomials. We assume that the group acts preserving the grading. So this is a graded ring. It's just the direct sum of all invariants in all homogeneous components of the polynomials. So it's finite dimensional spaces. It's a graded ring, very good. And then it's Noetherian, as we just proved. OK. Now the rest. The rest is clear because of exactness of the invariant functor. So we have G acts on R, which is finitely generated. OK. Of course, there could be a problem that because generators are not G invariant. So we just take a finite dimensional subspace by acting on G. So we suppose that generators are G invariant. If they are not, we just take all vectors in generators and add their G orbits. We obtain a set of vectors which generate G finite and G invariant. Good. So then R is a quotient of the polynomial ring. This is our generators. So x1 dot xn. This is a space of generators. Quotient by some ideal I. Good. Then Rg is C of x1 dot xn invariant. This is already finitely generated, as we proved in the previous slide, and this is Rg. It's an ideal. Doesn't matter, because the quotient by an ideal, I mean, this is Noetherian already, so the ideal is finitely generated. That's all. So the idea is just you use exactness, and if you have a quotient, you apply invariance to both. I mean, A This is exactness. A by B, G is A, G quotient by BG. This is precisely exactness of the invariant factor, or factor of invariance. We used it. We obtained that the quotient is finally generated. That's all. Thank you very much. Sorry for taking extra 8 minutes. Next time I won't. I just didn't expect you to have zero representation theory. Many people have it already, so sorry about this. But please look at the book of Sarah. It's such a nice